And thank you very much. So he's actually from, he's sort of a UWA, sort of, because he's stuck in China. So he's physically in Changzhou, I believe, and but he's a student at the University of Western Australia, and he's speaking on vertex-primitive s-arc-transitive digraphs for almost simple groups, and the goal is to show that S is at most 1. Over to you, Lei Chen.
Yes, thank you very much. Today, I think I will talk some results about a recently finished paper by my supervisors, Professor Michael Giudici and Sherry Prager and me. And if we take a glimpse at the title of the topic today, which is Vertex-primitive s-arc-transitive digraphs of almost simple groups, well, I have to admit that it is a bit of long-winded and there are many terms to be defined. Well, the very first thing I'm going to talk about is a digraph. A digraph is the abbreviation for the directed graphs, and it consists of 2 parts: the vertex set V and an anti-symmetric non-reflexive relation A defined on V. A is some sort of set consisting of some certain ordered pairs. And since A is anti-symmetric, which means that if UV is a pair in A, then VU is not a pair in A, and the non-reflexivity of A implies that there are no diagonal pairs UU in A. And for each pair UV in A, we write it as U to V, and U to V is also called an arc, and so that A is the so-called arc set for this digraph gamma, and sometimes a arc is also called a 1-arc, and the S-arc in gamma is simply the amalgamation of S1 arcs in gamma for S is greater or equal to 2. And here I will provide a very simple example to illustrate what is a so-called digraph. And we first found that there are 3 vertices, V0, V1, and V2 in this diagram. And there are 2 arcs, which are the arc from V0 to V1 and the arc from V0 to V2. It is easy for us to check that this diagram just satisfies all the conditions for being a digraph. The automorphism group of a digraph gamma is defined to be the set of all permutations in the symmetric group on the vertex set V that fixes the arc set A setwise, which means that for any element G in alt gamma and UV to be an arbitrary pair in A, then UGVG is again a pair in A. And for a subgroup G in alt gamma, we say that G is vertex transitive if G acts transitively on the vertex set V. And we say that G is arc transitive if G acts transitively on the arc set A. And similarly, we say that G is s-arc transitive if G acts transitively on the set of s-arcs. And we have to be aware that for a random digraph gamma, even alt gamma is not necessarily equipped with any of these 3 properties. And to see that, let us just go back to the last page and see our example. Let us consider what is the automorphism group of this digraph. Well, first, it must sit in the symmetric group on the 3 vertices V0, V1, and V2. And on the other hand, it fixes the arc set A setwise, which means that it either, the elements in alt gamma either fixes or swaps the 2 arcs V0 to V1 and V0 to V2. Therefore, the only non-trivial element in alt gamma is the transposition on the 2 vertices V1 and V2. And so that we conclude that alt gamma is generated by this transposition, and therefore is isomorphic to C2. And it is clear that alt gamma acts arc-transitively on this digraph as the transposition on V1 and V2 will transit the 2 arcs. However, V0 is always fixed by alt gamma. Therefore, or the gamma is not vertex-transitive. Well, the next thing I'm going to talk about is a primitive group, which is sort of cliche to everyone here. And for a transitive permutation group G acting on a set omega, we say that it is a primitive group if it does not preserve any proper non-trivial partition. And subsequently, a digraph gamma is said to be G vertex primitive if G acts primitively on the vertex set of gamma. However, this definition here for primitivity is a bit of abstract and sometimes not so useful in practice. So I will give an alternative statement for primitivity, but which is much more pragmatic to check if or not a group G is primitive. Here is a statement. So that we've got one transitive group G and it acts primitively on a set omega, then which means that the point stabilizer GV is maximal for any point V in omega, which means that if we would like to check if or not a transitive permutation group is primitive, it is sufficient for us to testify if or not the point stabilizers in G is maximal or not. And now we have already witnessed what is a so-called vertex-primitive digraph. However, for a given group G, we still have no clue of how to constructing such an example. And here I will provide some method of doing that. And our method is based on this theorem. Suppose that G is transitive on a set omega and alpha is a point in omega. Then the action of G on the set omega is equivalent to the action of G on cos G, G alpha here. Cos G, G alpha just refers to the left coset of G alpha in G. Here G alpha again means point stabilizer of alpha. And here is our construction. I'm so sorry. Say now we are given a group G. And remember that the point stabilizer in a primitive permutation group is always maximal. So we also pick a maximal subgroup H in G. And we will also pick one element little g, such that G sits in the set G minus H. And the vertex set of this digraph is simply the left coset of H in G. And the anti-symmetric non-reflexive relation A is defined as follows. And the last thing is the action of G on V is by right multiplication. Remember that the last term appeared in my title is almost a simple groups. One may have already know what is a simple group, which is are those groups where it does not have any proper normal subgroups, which means it does not have any normal subgroups other than identity and G itself. And I think the easiest examples of simple groups are those cyclic groups of prime orders. However, they are not interesting subject in this in this project. For a group G, we define the circle of G to be the product of all minimal normal subgroups in G, and we denote by soc-G. And therefore, we are able to define what is an almost simple group. A group G is said to be almost simple if the circle of G is a non-abelian simple group. And to study the almost simple groups, it is important for us to know the classification of almost simple groups. And according to the definition of almost simple groups, we know that the classification of almost simple groups is hinged on the classification of non-abelian simple groups. And in the beginning of this century, with the two publications by Asperger, we may regard the proof of classification of simple groups, finite simple groups complete, and all of the non-abelian simple groups may be divided into 4 big categories. The first one is classical groups, and there are several types in these big categories, say the linear group, the symplectic group, the unitary groups, and the orthogonal groups. And the second type is alternating groups, I think, which is quite familiar to everyone here. And the third type is exceptional groups of Lie type. Here in my recently finished paper, we investigate two families of these category, which are the Stucky groups and the small Lie groups. And the last type of non-abelian simple groups is sporadic groups. This family is a bit of special because every family member of this category are finite, and there are 26 of them. And since we are going to study the vertex-primitive s-arc-transitive digraphs, so we may be curious about the behavior of S and asking how large can this S grow. So we are going to seek the upper bound for S, and in 2018, Judici and Shah, they managed to show that if we would like to find such an upper bound for S, then it is sufficient for us to determine such an upper bound when G is almost simple. And we make the following conjecture or guess that all the vertex-primitive digraphs are at most 2 arc-transitive. This is because that the examples of vertex-primitive highly arc-transitive digraphs are fairly rare, and the only 2 arc-transitive vertex-primitive digraph example has been constructed very recently in 2018 by Judici, Li, and Shah. And this was constructed with G when G is a linear group. And here P does also satisfy some restraints. If I didn't remember it wrongly, it should be P is congruent to plus minus 2 mod 5. And the point stabilizer here is A6. And this belongs to the non-geometric maximal subgroups of the linear group. And in 2018, Judici, Li, and Shah, they, I think just shortly after they managed to find that 2 arc-transitive example, they did also manage to show that such an upper bound for S is at most 2 when the circle of G is a linear group. And 2 years later, 3 Chinese scholars, Pan, Wu, and Ying, they also showed that such an upper bound for S is at most 2 when the circle of G is alternating group, except for one subcase remains open. And inspiringly, I think just 2 or 3 days later, another 3 Chinese mathematicians, they just fill the gap left by Pan Wu and Ying. And in my project, we managed to show that, managed to find the upper bound for the Stucky group and the small Lie group. And I must introduce something about them, but due to the limitation of time, let me just fumble around a lot of details. And all of my construction here is based on the Robert Wilson's his construction. And first of all, we must know what is Q. Q is an order power of 2, and the order of S at Q is given by this. And Stucky group was firstly discovered by Michel Stucky in 1961 or 1960. And the very unique and special property for Stucky group is that it is the only non-abelian simple group whose order is not divisible by 3. And it acts on a 4-dimensional vector space. Of course, it does also satisfy some other complicated multiplicative relation, but I won't extend it here. And I think there's a very nice property of Stucky group, which is especially useful for our project, which says that it acts 2-transitively on the left coset of the maximal parabolic subgroup P in S at Q. Why is this useful? Because this implies that P can never be a point stabilizer, as all the digraphs generated by P are actually graphs. Here, let's just quickly go over all the maximal subgroups of S at Q, because they are all the possible point stabilizers or vertex stabilizers. The first type is maximal parabolic subgroups, which I have already introduced on the last page. And the second type is of dihedral type. The third and the fourth one are the Frobenius one. The last type is subfield stabilizer. Next, we are going to look something about the regroup. And there's one important reason why we did do the research on the small regroup and the Suzuki group together in one paper, as they just share lots of similarities. Say that, for instance, the outer automorphisms are all field automorphisms, and the subgroup structure of maximal subgroups of these two types of exceptional groups are fairly similar. So lots of methods can be applied together. And for the small regroup, Q is some order power of 3, and the order of the small regroup is given by this. And it was discovered by Ramkid-Ree in 1961. Also, I think the birthday of these two groups are fairly close. And it acts on a 7-dimensional vector space and satisfies some certain multiplicative relations. And this is based on Robert Wilson, his construction. And just like the Suzuki group case, it also acts two-transitively on the left coset of the maximal parabolic subgroup in ReQ, so that we do not need to consider about the maximal parabolic subgroup case for the small regroup. And the maximal subgroups for the small regroups are as follows. The first type is still the maximal parabolic one. The second type, I think it is the centralizer of one involution, a involution. And the third type is the full group normalizer. The fourth and fifth one are the Frobenius ones. And the last type is of subfield stabilizer. So here is our main theorem. We state that suppose that gamma is a G vertex-primitive G s-arc-transitive digraph such that the socket of G is a Suzuki group or a small regroup, then such an upper bound for S is actually 1. And indeed, this S can attain its upper bound 1 as we constructed examples where G vertex-primitive G1 arc-transitive digraphs for both a Suzuki group and a small regroup. So here is some of our future prospects. I think the first one has already been achieved fairly recently. Finished the remaining case in AIN. It was just posted in arXiv 2 days ago. And also we do want to explore something about classical groups, the symplectic group PSP2KQ, and maybe the large regroup. Yes, thank you very much for watching my slides. Do you have